Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're going to be taking a look at this oddball computer. It's a VTech Laser Color Computer 200. This computer was sent in a while back by Tommy of Arctic Retro. It's something that was never sold in the US that I'm aware of, and I think it was sold in other markets around the world, and it's an interesting little computer. I don't think this works, so in this video we're going to take a look at this computer, we're going to read up a little bit about it, and then I'm going to take this apart and we're going to see if we can get it working. So without further ado, let's get right to it. Now on first blush, you might look at this and think that this is a ZX Spectrum clone. And here's a ZX Spectrum for comparison. And the keyboards on both of these are similar size, and the layout is also very similar. They're both rubber keys with a very similar feel, space bars in the same location, and they both have shortcuts for basic commands, which I'm assuming on the Laser works in a similar way to this, where you just push R and you get the command return. Although on the ZX Spectrum, you get run. The case color on the Laser 200, that's a pretty pleasing kind of off-white beige color, brown background around the keyboard. Take a look at the colors that are available on this machine, and if you are familiar with your graphics generator chips, you may know right off the bat what type of graphics chip is inside this machine. These colors are very unique and specific to a certain chip. Condition-wise, the Laser is in absolute mint condition. It looks like no one has ever used this thing. On the left side of the machine, there are no ports. But on the back, we do have some ports. Starting from the left, we have DC 9 volts, center positive. There's a tape jack. Next up, monitor output, which I'm assuming is composite video. And then we have two edge connectors, which are not labeled. It does appear that maybe there was a cover of some kind on here at some point. There are little holes. And on the far side, we have a TV jack, which will be RF output. On the right side of the machine, we do have what looks like was the power switch, and it is no longer installed. It says on or off. Going to the bottom of the machine, the serial number is interesting, 042042, and we have the stickers for Video Technology Limited and Laser 200 Color Computer. Copyright 1982, made in Hong Kong. Now I'm noticing the screws are removed from the machine, and there's something floating around inside, and I have a feeling I have taken this thing apart, and yes, the case just lifts off. Before we take this apart and try to test it out, let's take a look online to see what the Laser Color Computer 200 is all about. Let's start with Wikipedia. The VTech Laser 200 8-bit home computer from 1983, also sold as the Solera Fellow, the Celtron 200, the Smart Alec Jr. in the US apparently, the TechSet TX8000A, and the Dick Smith VZ200 in Australia, New Zealand, and also the VTech VZ200 in the US and Canada. Now, in case you're not familiar with the VTech, they're a Hong Kong-based company that made a whole line of computers under the Laser brand, including the Laser 128, which was an Apple II clone, sold very well here in North America, and a whole line of IBM PCs. I don't know how far they went with the PCs. I have a Laser 8086 machine upstairs called a Laser XT Turbo SL, something like that. I think VTech dropped the Laser name around the time of XT class machines, like early 90s, and may have continued on with a different brand name. But VTech themselves, still alive and well today, they made a ton of kids' computers, basically low-end, kind of toy-like machines, really mainly designed for kids to get them used to computing. A lot of them had little LCD screens on them. Some of them were pretty powerful, where they actually had basic interpreters. You could plug it into a monitor and it has a full GUI. And I think this Laser 200 machine was designed to really capture the low-end computer market, really obviously copying from Sinclair with the ZX Spectrum. You know, there's too many similarities between these two things for it to be coincidence. Now, it mentions in the article that the Laser 110 was a development of an earlier monochrome TRS-80 clone, and further development introduced the Laser 200 and 210, which were similar to the EACA Color Genie and the Mattel Aquarius. The Laser 200 was discontinued in 1985 and replaced by the Laser 310, or the VZ300. Here's a photo of the Laser 310, and the keyboard layout appears exactly the same except the spacebar is in the normal spot, and obviously we're dealing with a much better keyboard, but even the power LEDs in the same spot, it leads me to believe that this machine is essentially just the Laser 210 or 200 with a better keyboard. And this is the Laser 110. Keyboard, very, very similar, but notice there's no colors on here. And the article said this was a TRS-80, probably Model 1 clone. So that means it would have a Z80 processor and just text mode with no graphics. Back to Wikipedia, it says that the VZ200 was released in 1983 and gained some following in Northern America. Okay. However, in the US, the Timex Sinclair 1000, which is just the Sinclair ZX81, undercut the VZ220 or 200, selling for $30. Yeah, citation needed. What was selling for $30? The Timex Sinclair? I don't think it was ever that cheap. I think this was, yeah, it says that it was released for $100 when it came out. I think it got down to 50. I don't think it ever got to 30, especially not in 1983. There's a claim here, 30,000 units of this machine were sold in Australia by Dick Smith in the first 12 months, so basically 1983 to 84. The machine was bought mostly for learning how to program, the only other widely available system in the same price bracket being the Commodore 64. I don't even know how much RAM this thing has, but I don't think it's very competitive to the 64 at all. In the UK, the VZ200 sold for a similar price to the 16 kilobyte ZX Spectrum. When it launched, TechSet, which was the distributor in the UK, claimed that it was £98, which was the cheapest color home computer on the market. Well, we all know how that went. The ZX Spectrum went on to be wildly popular. It says 5 million were sold, and it came out April 1982, so a year before the Laser 200. Now in the UK, it says here that it competed on price with the 16 kilobyte ZX Spectrum. If we look how much RAM this thing has, it says 2 to 22 kilobytes. I don't actually know how much RAM this has, but if it's got 2K, that's hardly competitive with a 16 kilobyte machine. When it comes to the successor, the 310, it just says here that it had more ROM and a software-based floppy controller. Hugely successful in China, with primary schools having Laser 310 sitting next to Apple IIe's. They had Apple IIe's or Apple IIs in China? I don't think so. I think there was an Apple clone, which I'm going to make a video about, a Chinese version that is. I'm pretty sure there were no actual Apple IIs in China. This whole Wikipedia article definitely needs a little bit of TLC. There's a lot of things said in here that I don't necessarily believe, and there's no citations. All right, let's talk about the specs of this machine. Right there, Zilog Z80, 3.58 megahertz. Memory, as I just mentioned, 2 to 22 kilobytes. That means there's obviously some amount of onboard RAM and capability of an expansion pack, probably that plugs into one of those edge connectors. 2 kilobytes of VRAM and 16 kilobytes of ROM. Now, when it comes to the graphics chip, the colors on the keyboard, as I mentioned, gives away that this has the Motorola 6847 video processor. That is the same exact chip used in the TRS-80 color computer, along with the Dragon 32, Dragon 64, and probably a myriad of other machines. And the graphics modes are weirdly limited in certain ways that result in games that have very bright colors, but very few of them. So here's a screenshot from Frogger for the TRS-80 color computer, and the color palette you have here is one of the graphics modes that is on this particular graphics chip, which means the graphics capabilities of this are going to be identical to what the TRS-80 color computer or the Dragons have. And this odd combination of the colors, which doesn't even include black or white, and you can't redefine these colors, mean that the games are interesting looking. No, there's another mode on this chip though that's a higher resolution graphics mode, and it does support artifact color, very much like the Apple II. But unlike the Apple II, it only supports 4 colors: black, white, blue, and orange. It's these colors right here. And at least on the TRS-80 color computer, every time you run the game, the blue and the orange can be swapped. I think it's something to do with the timing circuit. They're not consistent. The Apple II, they're consistent, but on the Coco, they're not. Thing is, this is an NTSC mode that will not work in PAL regions. So that means if the Laser 200 even supports this mode, which I'm sure it does because it's the same graphics chip, it's not going to support the artifact color if the machine is PAL. And I think because this was sent in from Norway, almost certainly this runs at 50 hertz and is a PAL machine. And actually, taking a look further down the article, it says that because there's only 2K of video memory, it doesn't even support the bitmap mode. So yeah, it's not supported on this machine at all. Personally, I've always found the graphics modes on the 6847 a little off-putting just because of those really garish colors that are very limited in the graphics modes. And then with text mode, not even having the ability to have white and black text, it just seems very weird. Looks like on this machine, sound support is essentially a beep speaker. And from a RAM perspective, Looks like it depended on your region. 4 kilobytes of RAM in Europe, 6K in North America, which was increased to 8K within weeks of its release. Throughout Australia and New Zealand, the initial releases were 8K, and a 16K RAM expansion was available, increasing RAM total to 24 kilobytes. The VZ200 was released with 18K of RAM, internally obviously. So an 8K system is 6K of RAM, 2K of video RAM, and 16K of ROM. And the memory could be expanded to 24K plus 2K video memory. I'm a bit confused by the fact it says an 8K system was really 6K of RAM plus 2K of video memory. So I suppose the original 6 kilobyte North American release had 4K of RAM plus 2K of video memory, and the 4K European release had 2K of RAM and 2K of video memory, because they're adding those together for some reason. Now, what's kind of unusual to me is the TRS-80 Model 1 even supports 48K of RAM, and the rest of the space is for ROM and the video memory. So it's a little confusing why 24K seems to be the limit of the memory on this. We'd have to probably look at the memory map to understand that a little bit better. And there's a picture of the optional 16K RAM expansion. That's the Dick Smith branding. Well, it appears that Laser was releasing peripherals that were compatible with both the 310 and the 200. Kind of tells us how similar those two machines were. Joysticks, cassette drive, light pen, plotter, printer, 75 baud modem, a word processor cartridge, 16K and a 64K extended RAM cartridge. So a 64K must have been using bank switching. Well, there was even an external 101 key keyboard for this device. 128 kilobytes of sideways RAM expansion, very much a BBC or Acorn thing to call it that. It just means bank switched, basically. Moving on to the 310, it looks like it was released with 16K of RAM internally, and the same 2K video RAM though. And yes, and then there we go, confirmed. It is completely compatible with the 200. It just really means that it had the upgraded keyboard and the internal RAM expansion. And then there's the Laser 100/110, which earlier in the article said it was like a TRS-80 Model 1, it even says that here. But it uses a 6847, which is the same video processor that's in this machine. But even though it had color capability, and it had 2K of video memory, the Laser 100/110 did not support color. Interesting. So it just was lacking color burst signal, I suppose. As far as the BASIC that runs on this, it seems to be BASIC 2, which is similar to the level 2 BASIC on the TRS-80, which makes sense. It's Z80 BASIC as well. And that's all there really is in this article. So kind of light on details, most likely because this machine was never massively popular. So I'm definitely curious if you watching had one of these, or used one of these, or saw one of these in use. Did you have friends with them? Growing up in the 80s, I had friends with all sorts of different kinds of computers. I did not know anyone who had one of these, and I never saw one for sale in any kind of shop. In Canada, that would have been the right time for when this thing came out. I got my VIC-20 in around 1982, and then 1984, 1985, that's when I got my Apple IIc. But I had friends with all sorts of different computers, TIs and whatnot, and like I said, never seen anyone with one of these before. It is time to stop talking and let's open this thing up, take a look inside. On the Wikipedia article, there was a photo. Oh yeah, okay. This is something that I did, I think. So that's screws and stuff. Oh boy, okay. We have a ribbon cable. The photo on the Wikipedia article showed a little bit of what was going on in here, and you can kind of tell this thing is extremely cost reduced. There's the power switch. Can I disconnect this keyboard? So it's a ribbon cable that's glued on. Interesting how it has a line here, as if they maybe originally designed it with a very small keyboard and a numeric keypad over there, because I don't see why this plastic separator is there. Let's try to extricate this from the case. And inside the case, oh, that must have been where the speaker is, glued down. Looks like it's just hanging off the board right there. Things look very clean on the inside of the machine though, otherwise. Okay, so looking at this, you can tell extreme cost reduction was going on. This is bodge-tastic. So the keyboard is soldered on with no freaking way to disconnect it. You gotta be kidding me. I mean, look at this big cap just hanging off. This is, I take it, a shielded cable. No, it's not. Mesh spring power, but these pink bodge wires are absolutely hilarious. We have a heatsink that's clearly for the voltage regulator. This will take unregulated 9 volts and bring it down to the 5 volts that this thing almost certainly needs. I don't know what this board is doing. I'm not sure. Maybe like the crystal, there's just like all of these adjustments and things. I think first thing I need to do really is desolder this shield so we can take a look at the ICs that are underneath. And I think I'm going to have to probably remove this keyboard from the board. I mean, I'm quite positive this thing doesn't work. Let's get the shield off first, then we'll plug it in to see what it's doing. Okay, I got the keyboard disconnected, and this is horrible. Absolutely horrible. In the process, one of the pins broke off. So that means I'm going to need to, I guess, cut this and trim it or try to extend that one pin. Wow, yeah, that's horrible. This is designed to go on probably easily in manufacturing. And after that, yeah, not really made for serviceability. Okay, now I got some of these ground straps off, but now I have to figure out where this is actually attached. These types of PCBs, the foil is very fragile, so it's very easy to damage the traces. So you have to be very careful. And like I said, this thing is designed to be put together cheaply, and that's it. So there we have it, the VZ200 exposed Z80 CPU. We have a 6116, that's 2 kilobytes of static RAM. These must be ROM chips, I'm assuming. Yeah, 2364, those are absolutely ROM chips. We have another 2 kilobytes of SRAM, and I'm gonna have to get this board off. Looks like there's a screw. It's attached with a ribbon cable, and the screws have a bunch of glue. How about on the underside? Might be easier. Yep, there we go. They can get those out. That's nice. They didn't want it to come off, I suppose. I should be able to lift this up. There we go. Wow. Yeah, there's some more glue on there. I was holding that down. So under this clock board, I guess that's what that is, 6847, so that's the graphics processor, and we have our 2K of SRAM. So this obviously is the European model, which has 4K, 2K of RAM, 2K of RAM. This is obviously for the video memory, 2K of system memory. Construction quality of this thing is, yeah, cheap, very cheap. But the positive thing is there are no custom ICs on here. Everything is replaceable. So if this is not working, hopefully it's something I can figure out and we can get it actually working. I noticed on this board there is a chip I don't recognize. This whole board is just so crappy looking. It's almost like what you would see inside one of those cheap transistor radios from back in the 70s. I'm wondering if this is doing the composite video decoding. The Motorola 6847, to convert this into composite, you need a little bit of circuitry, an RF modulator, which incidentally, there is a channel selector. I think on the bottom of the case it had channel 3 and 4. Look at the bodges. I mean, this is wild. The speaker connection is just like bodged on. I'm blown away by this thing. Okay, for powering this up, I'm gonna start with the bench power supply. I can see there's a 7805, so we are gonna give this about 7.5 volts. And I'm gonna limit this to 390 milliamps, so just picked a random number. And we'll use the RetroTink for video capture, because we wanna see if this thing's outputting anything. Let's double check. I have the power supply turned off, that the ground is actually going to the ground. Okay, yes, we have continuity. And then the positive lead should make its way, if I move these caps out of the way, over to there. Okay, good. So polarity is correct. And let's see what happens now. Okay. Okay. It's freaking out. It is totally freaking out. But that's good. What we're seeing there, even though there's a bit of rolling in it, incidentally, it's using 640 milliamps at 7.4 volts. What we're seeing there is absolutely the text mode coming out of the video processor here, or the video graphics chip. The two modes available are a dark green background with a light green text, or vice versa, or a dark orange or light orange background with the opposite orange text. Let's see if the power switch is working properly. Yes, it is. All right, let's check the output of the regulator. 4.947, good, you can see that, so that's good. We're not overvolting the system. Now, what's wrong with the system right now? There could be plenty of things. One thing I am curious about, are we running NTSC or are we running in PAL? 50 Hertz, okay, we're running in PAL. I'm just noticing the uptime is -1 days. Okay, RetroTank, yep, you're great. Now from a problem perspective, there could be all sorts of issues. The CPU could be dead. It's not overly hot. We could have a bad ROM chip. We could have a bad RAM chip. We could have all sorts of things that aren't working properly. But the machine also just might be stuck in reset. So it's time to bust out the oscilloscope and get to troubleshooting. All right, first thing I want to do is let's see if there are schematics. I found this VZ200.org. I think it's the comprehensive site that has everything there is to do about this computer. So if there's no schematics here, probably there are none that exist. Let's see, I'm looking at a manual, instruction manual, technical manual, complete single PDF, freaking great, Dick Smith. Yeah, should be good enough for what we're doing here. There's the memory map. I was talking about that earlier. So yep, on the Z80, the ROMs always exist at the very beginning of the memory space, unlike the 6502 where it's up at the top. Reserved for ROM cartridges, 10K. Keyboard, so the peripherals like the keyboard, cassette, and speaker are memory mapped and not I/O address mapped. The Z80 is like a 8088, has I/O addresses, so you can directly talk to things outside of memory space, but they're not doing that. Inbuilt user RAM, 6 kilobytes, I guess on the motherboard, reserved for memory expansion modules. The RAM is not what we're talking about now. We're trying to figure out how to get this thing booting. So it looks like it uses a latch for various outputs, including speaker A, speaker B. So probably one of those is used for the cassette interface, and the other one is going to be used for the speaker. Although actually no, it's a push-pull fashion with bits 0 and 5. To make the speaker sound a note, it should toggle bits 0 and 5 alternately. Bits 1 and 2 are used, right there, cassette output. Anyways, that's used for the cassette. Probably works in exactly the same way. You would alternate those two, and it generates 175 millivolts peak to peak. VDC mode, I think that's an input into the graphics processor to change the mode. So let's just try to find what we're looking for. The schematics. All right, I have the chip clip connected to the Z80, so I can easily clip the oscilloscope probe onto it. I got to look at where pin 1 is. All right, it's closest to me on the left side. Because I don't work on a lot of Z80 stuff, I'm not super familiar with where everything is. Remember, there are basic things the CPU needs to run. You need reset signal that works properly, like comes out of reset. You need a clock signal, you need voltage. Without that, it's not even gonna attempt to run anything. And what we're looking at on the computer when we turn it on could just be the dead CPU, for instance, easily. All right, let's see what happens when we turn it on. We do see a signal. And let's just adjust the settings, get them looking good, 1 volts per division. And I see how it's alternating. That's probably because I have trigger set to both. Yes, rising or falling, we'll set it to rising. And we are getting 3.58 megahertz. Perfect. That is working. I think we can pretty much assume that the voltage is good. We already checked the voltage regulator, so I don't need to check the voltage pin. We need to find the reset signal. Read, write, interrupt, clock, MREC, non-maskable interrupt, wait. That's just pulled up to 5 volts. I don't know what pin 25 is not labeled. Pin 26 is not labeled. Is that the reset? That's the reset circuit. Okay. I'm looking at the motherboard, I'm thinking, where's those drivers for the reset circuit? There's no silkscreen markings at all, because that would cost like an extra 2 cents or whatever. All right, I'm on pin 26. Let's see what happens when I turn the computer on. I think that's fine. I think it's totally working fine. We need to go look at the data sheet real quick. I don't know if it's reset high or reset low, but I'm assuming, like the 6502, the system is in reset when this pin is held at ground. And it looks like when I turn on the system, I see it held for a second, and then it goes up. If we just take a look at a pinout diagram, reset has a slash in front of it. That means, oops, the probe fell off. That means that it's reset low. So when that signal is at ground, the CPU is in reset. So I'd say the reset circuit is working just fine. Now again, because I'm not super familiar with the Z80, we have this slash wait and slash halt. Both of those sound like if either of those are held low, that the CPU may not run. So let's take a look at those pins. So I'm on slash halt, and that is low. Let's turn the system off and on. Let's see what happens. That might be an output. Oh. Okay, so 4.3 volts, but it was low a second ago, and now it's not. Let's power cycle the computer again. Ah, now it is low. Let's take a look at the manual. Wait is an input, hence the arrow pointing into the CPU, but halt is an output. So that just could mean it's crashing and it's going into that halt mode. So I moved over to pin 24, which is this wait input. Let's take a look at what that looks like. Okay, that's high, which is good. That is active low, which means if it were down at ground, potentially the CPU couldn't run. We know reset is good. I don't think interrupt or non-maskable interrupt necessarily matter. Let's take a look at these, this bus request signal. I think this signal is like a DMA function. In fact, is this even hooked up? Pin 25? Pin 25 is pulled up to 5 volts. Oh, so is wait. Okay, and non-maskable interrupt. I guess none of those are used. Okay, so we've determined the reset signal is good, 5 volts is good, clock signal is good, the wait signal, which could potentially stop the CPU, that's looking good, as is the bus request signal. Like that's for DMA, which obviously not used, that's just held at 5 volts. Let's take a look at the address lines. Address line 0 should have a bunch of activity on it. Let's look at pin 30. And there is pin 30. So we have activity, but it's definitely stuck. The CPU is absolutely stuck. Oh, it does a little bit of something there. So as it executes code and goes through the ROM, there should be some activity, and then it just immediately stops. Ah, but that time there was a little bit more. So remember the first time we turned it on, it was kind of glitching a little bit. I wonder if that was the CPU attempting to run a little bit. So there's the video that's coming out of the machine though, and it doesn't look like much is happening. The RetroTink takes a while to synchronize. I think what we should do is just take a look at all the address lines. If there's a problem on an address line, then it's not going to be able to address the ROMs properly. So I'm just going to look through these pins manually, and we're going to see if any of them look suspicious. I mean, they're all stuck, but I just don't want to see anything that's like stuck at 2 volts or 1 volt or something like that. This all looks normal. Now going back to pin 1, I'm going to reset the power. Okay, I can hear the speaker was making a ticking noise. So it's kind of random what this thing is doing. So now this pin, which is pin 3, address line 13, is doing nothing. Oops. Very, very random things are happening. All right, this is pin 4, address line 14. Yeah, that's funny that the speaker is ticking. I'm assuming what's happening is it's hitting that latch that drives the speaker. And that's probably when the screen was glitching out. Okay, well anyways, address lines are all looking perfect. So we need to check out the data lines. Thanks Dialog for not putting the data lines in any kind of order. I'm on pin 7. That's data line 4. It's not stuck at a weird voltage, but it definitely is weird. Very weird. Let's power cycle it. Strange stuff is happening here. This looks strange. Like, is that the clock signal leaking through? That's got to be the clock signal leaking through onto the data lines. This is the clock signal right there. So see the period that we're looking at? If I go back to that data line, that's very clock signal looking. This line, I mean, it's going high, it's going low, but then what are these weird things here? I don't know if the data bus is pulled up or not. There's that, what looks like a clock again, leaking through. That's another data line. Looks pretty funky. Looks pretty funky. This is D7, pin 13. Looks weird. And that's pin 14, data line 0. And then this one is 15, data line 1. All right, well, none of those look like they're stuck low or high, so that's good, but I don't like that we saw what looks like clock signal leaking through. Now, if we think about the clock signal does not make its way to any of those ROM or RAM chips. It only makes its way to the CPU, and most likely it makes its way over to the graphics processor. This is a big page that is not scanned in one piece, unfortunately. There's the data lines going into 6847. And it looks like the 6847 talks to its own SRAM chip. That's the 2K. over the same data bus lines as the rest of the system. So it makes its way over here and back to the 6116. Now I'm noticing, oh, okay, this is good to know. There's a LS245 that separates the video subsystem from the rest of the system. So that's going to be worth us checking to see if the enable signal and the direction signal are generated correctly for the LS245. So the 6847 can address its SRAM directly, but through these 6.8K resistors, it's connected to the regular address bus as well. And that's because the 2K of video RAM is available to the CPU and to the video graphics chip. And I would have thought that we would have had like a bus transceiver between these address lines, not resistors, but it's relying on resistors to prevent a bus conflict, I suppose. Weird. Now, if this LS245 weren't working properly, I think what would happen is the system might boot, but it wouldn't be able to update the screen. The system clearly is not booting and working properly, right? Because we see such random things happening on the address lines that I don't think that's our problem. And scrolling down the schematics, we have some select logic or something happening there. And then this is obviously maybe on that little board. TBA, that's that little chip that's on that board, that little, what I thought was like a radio board. And yes, this is what converts the video output of the 6847 to a normal-ish video signal, or at least a chroma signal that can then go and be turned into a video signal that can be displayed. So this is one of the things about that 6847. You need a somewhat complex circuit just to support color. It's probably why the Laser 110 did not have color, is this board was just omitted. And I think this TBA 520, there's a different version of it that you use for NTSC color, and there's a Motorola part as well for that you find inside the Cocos. And it appears these gates all generate a video clock. And that probably goes to the 6847. A DRAM line, I bet you this comes on to tell it, hey, the CPU is talking to the RAM, so don't try yourself. Video out, component, video clock, yeah, okay. That's interesting. So that means that the 6847 does not run on the normal CPU clock. Let's take a look at pin 35, the clock signal on the 6847. I want to see if, well, I don't even know what frequency that runs at, because we need to figure out what's leaking onto the data bus. All right, here's our clock. Same 3.587, but then there are gaps. My feeling is these gaps probably have something to do with how the CPU and the video chip share that data bus and address bus and the video RAM chip. Here's U3, which is a LS139, typical address decoder. ROM 0, ROM 1 chip select lines. Looks like we have a couple DRAM chip select lines. 7000 and 7800. 7000 I think goes to, well, it goes into a gate. Yeah, this is what's connecting to the video RAM, right, through this gate. And the chip select signal does go to the enable pin on the LS245. It says here program RAMs are on a supplementary circuit. Ah, right here. Okay, so we have an extra 74 LS138, and we have 3 SRAMs. This is the additional memory that this machine does not have. This has 2K of program RAM, and obviously we're talking about 6K right here for the Australian version. Ah, there's the 78XX. So most likely that signal just goes directly into the 6116 that's next to the CPU or next to the ROMs on this board. That is just for the main program memory. And there's some additional select logic to enable operation of these extra chips. All right, well, I think our biggest smoking gun so far is what looks like clock signal leaking onto the data bus. And it could really only be coming from 2 chips, the CPU or the 6847. Now, the data bus lines of 6847 are connected through an LS245. And what I forgot to do is check the chip enable line on that chip. So we gotta do that first. But normally, if it's operating correctly, that chip won't even be enabled unless the CPU is trying to talk to the video memory. And it's not most of the time when it's talking to the ROM. So that chip is disabled. Therefore, the 6847 is not even connected to the rest of the data bus. So that weird clock thing probably is not coming from the 6847. Let's check the chip enable line to the LS245, and we can check both sides of that chip. We can look at what is facing the CPU and what's facing the video chip. So first let's start with the enable pin, pin 19. So power on the system, it is not being enabled at all. I'll reset the power, off, on, nothing. So I'm currently clipped to data line 7 facing the CPU. All sorts of activity here. And I'm now clipped onto pin 2, which is data line 7 that faces the video chip. I'm assuming that's the video chip refreshing the video RAM. It needs to do that to draw the text screen. And if we power cycle the computer, it's going to look the same every time. Yeah. All right. So I think what this means for me, I think the problem with this computer, and this is guess, I think it's the CPU. Just looks a little suspect with that clock that's leaking through, and it's got to be coming from the CPU. I'm just feeling any of these ICs just to see if anything is super hot. And no, everything seems completely cool, including the CPU. I mean, it's slightly warm, but barely. I think the CPU is the problem. I really do. So I think I'm going to heat up the desoldering iron, and I'm going to socket this so we can test another one. Okay, the socket is in. Obviously, I had to remove these wires and then reattach them, which is why I had a picture on my phone. 2 of the pads came off because this PCB is the lowest quality PCB imaginable. So 2 of the pads on the backside, they don't connect to anything on the backside, came off, but I made sure to flow solder directly through, and I double checked it. It was like one of the pins over here and one over here, and they are connected to the traces. Getting the chip off was pretty difficult, a lot harder than normal. I was using plenty of hot air, but it did not want to come free. But I didn't rip any traces, and those pads on the back, even though my desoldering iron was set to the minimum temperature it can work at, 350 Celsius, it still just lifted those pads immediately right off the board. So it's a very low quality PCB. As for testing this machine, here's a Z80 CPU. I think I should work. I had it sitting off to the side. Usually, if it's bad, I'll mark it as such. Double check, no pins bent. We'll do the usual. Before plugging the video in, let's hook up the oscilloscope probe to the address lines, and let's see if we see what looks more normal on the activity there. Here we go. Well, yeah, I'm gonna say that is not any different. Oh, look at this. This is data line 0. There's that same thing. Okay, I was totally wrong that this CPU, the one I took off, was not bad. And now I'm on the 245, which is connected to the video subsystem. And obviously we're looking at the CPU side there. Let's look at the side that faces, oh, wait, what? This is the side that faces video chip now. Let me just explain what's going on. I didn't really explain it very well in the footage when I recorded this because I'm pretty confused, as you can probably tell. Since I saw what looked like clock leaking again on the data bus lines, even though we changed the CPU, I was going back to thinking that maybe it was the video chip that was causing this. So I'm looking at the LS245, which I think connects the CPU to the video subsystem, and it doesn't seem like I'm seeing the correct signals. I'm now seeing the same signal sometimes on both sides of it, which doesn't really make sense. And then other times I don't see any signal on the CPU side, but I see a signal on the side that should be facing the video subsystem. Pin 17, data line 5, that goes towards the CPU. See, comes down here and it shoots off over to the CPU. That's pin 17. 20, 19, 18, 17. And yet, there it is, which doesn't look like anything. These schematics must not match this board, or I'm looking at the wrong LS245. There's another LS245 right here. I saw this one and I kind of assumed this was the one that handled the video subsystem, but it must be this one that handles the video subsystem. And I guess there are 2. And looking at the traces on the board, it's absolutely this one. That is the one that's in play for the video subsystem. It is not this one at all. Okay, whoops. And I see the traces, and I'm sorry, the battery died in the camera, so I can't show it right now, but the traces from this go to the video chip and the SRAM chip that is associated to it, the video RAM there. And looking at the schematics, the chip I was looking at is this one. It's not even labeled on here, but I'm sure that's an LS245. That goes to the freaking keyboard. Yeah, it's gotta be. It's gotta be that. And yeah, looking at the board, I see these pull-up resistors for the keyboard matrix hooked up to that, that LS245. Okay, well, that changes everything here, because obviously we might be having a problem with the 245, this one, because the 6847 must be trying to scan the VRAM chip all the time. And if the LS245 is being turned on when it shouldn't be, or it's bad, it could be causing bus conflicts. And that could exactly be what we're seeing here. Okay, so I know you can't see it because the camera died, but I am currently on pin 1 direction signal of the correct LS245. And we turn it on, and there was some activity. So that would imply that the CPU at some point was trying to write to this chip. Okay, fair enough. Power cycle it again. Yeah, there's some stuff happening there. Now let's go to pin 19, the enable pin. And currently it is not enabled. So we'll power cycle this. Okay, there were little spikes there of activity. We'll zoom out, try this again. Like just a blip there. Let me cut in here and explain a little bit, because I didn't do a very good job in the footage because I'm confused. What's happening normally when the system is idle is a 6847, that's the video chip, is regularly redrawing the entire video frame. It's outputting at 60 or 50 times a second. And every time it does that, it has to read the contents of the SRAM to display them on the screen. And those are the exact signals we're seeing on the data bus lines that are specific to the video subsystem. That's on the other side of the LS245. So just doing normal operation, you're going to have a bunch of activity that's dedicated to just refreshing the video screen. There's a signal that goes to the 6847 that says, hey, stop reading from the video RAM, I'm about to write to it. And at that point, the LS245 connects those data bus lines for the video subsystem to the CPU data bus lines, and then that allows the CPU to write to the SRAM, and then it releases it, and the 6847 goes back to just reading the contents of SRAM so it can display it on screen. All right, so let's look at the data lines. We're on pin 2. This is data line 7. It faces the video chip. I don't think that's the same frequency as the clock. Let's check a look at the clock. So, all right, so there's pin 6 on the CPU. That's the clock. So that's that high frequency thing that we think we're seeing on the data lines. Let's power cycle it. Let's try to get back that clock frequency. Ah, there it is. So if we zoom in a little bit, there's that clock. And if we look at that, it's actually, doesn't that even seem higher frequency than the clock? It does. So there it is. And this is the clock. Oh yeah, okay, it's higher frequency. Can the CPU generate something on the data line that's even higher frequency than the clock? Anyhow, back on the 245 that's facing the video RAM and the video chip, that's the frequency that we're seeing there. I mean, that looks completely normal. Let's check all of these lines. All of this seems fine. I'm assuming what you're seeing there is like some garbage in the video memory. That's why the screen, when it's not initialized like it is now, there's some random characters. Now, when these LS245s go bad, occasionally it can always be selected where it's connecting the two sides together, things like that. I don't think that's what's going on, because this is the side of the data bus that faces the CPU, and it looks completely different than what we see facing the video chip. Well, I'm back after a bit of a break. I needed some time just to kind of think about what's going on with this machine and try to arrange my thoughts in a way that would make sense for the video, but also for myself from a troubleshooting perspective. Clearly, the fact that the CPU runs for a little bit and then crashes and it's doing all sorts of random things tells us that there really is a problem executing code. Now, the reason why I was going down the LS245 path is that bus conflicts by a malfunctioning LS245 can absolutely cause issues with the CPU being able to execute code. But, as I said, I think the 245 can be ruled out entirely, so that is not the problem. And what that really leaves us with is the ROMs. That's the very first thing that happens when you first power on a computer. It executes code out of the ROMs, and then that sets up the computer, initializes the video, does whatever, and that seems to be what's failing. Now, one thing I hadn't tried, and we should try right now, is we should see what happens when we turn on this computer without the CPU installed. And the reason why I say that is because when we power on the machine and we see that activity that looks normal for just a split second, we also see activity going to the LS245 that is for the video subsystem. That implies that potentially some ROM code is actually running, and then maybe the ROMs are bad and that causes the system to crash. And if the ROMs are bad in weird ways that cause random data to be read out of certain locations, well, then that can produce very unpredictable results like we're seeing right now. And remember, when we turn on the system with hooked up to video, sometimes we see what looks like a graphics mode, and sometimes we see a text mode, and sometimes it's flickering and doing different things. And I want to know for sure if that randomness that we're seeing there is coming from the CPU trying to do things to the computer, or is that just happening on its own, even without the CPU executing any code. So let's give that a try. So let's just pop out the CPU, and I did put back in the original Italian CPU, since we know that this chip is most likely good. We saw the same symptoms with this Zilog one. Okay, CPU's out. All right, and let's turn this thing on. I'll use the power switch. Let's see what we get. So we're in graphics mode and there's no color. I think what's happening is this ribbon cable is failing. It connects this little extra board. This obviously is what's decoding the color information, the chroma, and I guess there's a bad connection here. So if I put my finger on it, there we go, we have color. But we're in graphics mode. I'm going to reset the power and power cycle this several times. And let's see if we see that text mode that we were seeing. Nope, that looks identical. I just want to look for that text mode that we were usually getting when the CPU was installed. No, absolutely nothing. Okay, it looks exactly the same every time. Let's pop the original CPU back in. Okay, now what do we get? Ah, there was a little bit of flashing. In fact, the colors look different. And that is something I think that is written from the CPU to the video chip. Let's keep power cycling, see if we see differences here. I have my finger on the cable. Oh, text mode. Right. Now this is actually very interesting. This implies that there is code being executed when the system is powered up. And remember, if you're looking at the service manual here, there is a latch. And this is what's controlling the sound, but also the video display mode and the background color. It doesn't say here what the latch chip is, but almost certainly latches, when you first power on the system, they default to high, a level of 1 for all of the outputs. It says the video display mode is controlled by bit 3. If bit 3 is a logic level 0, it will operate in text mode, and if it's 3, it will operate in the high-res graphics mode. High-res graphics mode is not the bitmap mode that this thing doesn't even support. It's just a higher resolution mode than text mode and supports those garish colors that I was talking about. And remember, the latches default to 1, and that means if there's no CPU installed, when you power up the system, this signal, VDC signal, will always just be 1 by default, which means it will always be in graphics mode. And it takes the CPU writing to that latch to actually change the output to a 0, which would then enable text mode. Which tells me that I think the CPU is executing code and it's trying to run the code that's in the ROM, and this is ROM 0, so it starts at address 0, which means this is the code that runs when you first power on the system. And I think some of this ROM chip must be okay, enough of it, to start writing to the latch, which switches to text mode, and then the system crashes. And the fact that consistently with the CPU out, it's just in graphics mode that looks exactly the same every single time really does confirm that it's the ROMs that have probably failed on this system. I think the next step before I remove the ROM chips, though, is to check the chip enable lines that go to the ROM chips. This is decoded from the address lines, and see if they're both selected maybe at the same time. That could create a bus conflict, or those signals look okay. So in the schematics, I could see that an LS139 was doing the decoding for the ROM and the RAM, plus some of the I/O stuff. It appears that is this IC. I'm assuming it's this one. And we can check that by checking the continuity. The two ROM select lines should be pin 4 and 5. So that's 4. And it should be pin 20. There it is. And 5 would go to this chip. Yep, okay. So that is absolutely what's decoding the ROM select or chip select lines or signals for the ROMs. So we'll just clip onto here. And let's turn this on. We should see normal activity on both of these lines, and we should never see both lines, the yellow and the red trace, low at the same time. The red trace is ROM 0, so that's the boot ROM, and the yellow trace is the other ROM chip. Well, things look good here. They're never both being selected at the same time, which is exactly what we needed to happen. And they both look good. So I think that pretty much tells us that at the minimum, I need to remove ROM 0, and we could try reading it in the Retro Chip Tester Pro. Now remember, when I flip this over, we have bodge-tasticness happening on the bottom side. This is the RAM, and these are the 2 ROM chips. And besides these wires, look at that, there's a jumper link crudely installed. And you know what, looking at the footprints, there are extra pins along the top row. I bet you this was designed originally to accommodate EPROMs, 2764s, same size, they just take more pins. And I say that because on a 2764, the top 2 pins both need to be at 5 volts, because pin 1, which would be up in this position, would be VPP, which you just need to hold up at 5 volts while you're not programming the chip. So we'll just check continuity. These 2 pins should both be 5 volts, and they are, and same with that. And I wouldn't be surprised if those bodge wires on the bottom are to switch around a couple of the other signals that are required because address lines are in slightly different position. A couple address lines are in a slightly different position with these chips versus the 2764s. Now with 2364s, the mask ROMs that are on here, it's very similar to the kernel ROM on the Commodore 64. There are EPROMs that you can get that have the same footprint and generally will work in place of one of those. And if you ever notice in my ZIF 64, I actually have a replacement kernel ROM that is the original footprint. I don't need an adapter to use it. The problem with those chips is they are very hard to program, and you need a very special programmer to program them, and I happen to have a Data IO 2900, which is a very expensive, fancy programmer from the 90s, but you can't program them on something like a TL866, at least not easily. Maybe you need some special adapter or something. I don't know. I never really looked into that. I also have a limited supply of those chips, so I'd rather not use them on this if I could just remove those bodge wires and then just use normal 2764s on this board. I have tons of those. So I think what I'm going to need to do is remove both ROM chips and unmodify it so that I can use 2764s in the board. The reason why I can't just do one of the ROM chips is that most of the signals on these ROM chips are all parallel together, exactly parallel. The only thing that's not are the 2 chip select lines, because there's ROM 0 chip select and ROM 1 chip select, so those run to the LS139. So if I undo the mods for one of the chips to use a 2764, it's going to undo the mods probably for the other one as well, which is why there aren't a similar amount of bodges on both of the chips. But these are the bodges that appear to be for the ROM adaptation. I think at the same time, because this ribbon cable's failing on this little color board, I'm going to replace these with wire lengths or length of flexible wire. That way this won't be a problem anymore. The ROMs are out. I did label these before I removed them. That one has a 0. That one has a 1, just so I know which was which. That was the 0, that was the 1. I've put in the larger sockets, and on the back of the board, you can see I don't have any bodges right now. I just removed everything that was on there. I also went ahead and installed a ribbon cable for the color board, and I also installed this right angle pin header for the keyboard so we can easily connect and disconnect that in the future. What will happen if we power this thing up without the ROMs installed in the board? Will we get the text mode, or will it just look like when the CPU was not installed? Place your bets. Let's turn this thing on. 3, 2, 1. I think that's the retro tank. I'm gonna reset the power on the retro tank. Okay, well, it's still freaking out there after resetting the retro tank. I didn't even recycle the power, and that's with the ROMs uninstalled or removed from the board. So my assumption that the ROMs are bad might not be valid, because we're seeing the exact same symptoms without them installed in the board at all. How about we use the Retro Chip Tester Pro to dump the ROMs? This can read 2364s. Luckily, I noticed this computer is fully emulated. There's a MAME image for it, so that means the ROMs are already dumped. So I don't need these to work, but let's just see if they do work at all. Okay, so it's a 2364, and these are 24-pin versions. So let's try to read this. Ah. So that ROM appears to be good, and it's in the database even. Wow. How about the other ROM? Same thing. Oh man, both of them work. This video is going kind of terribly right now because obviously I accused the CPU being bad and it wasn't. I accused these ROMs of being bad and they're not. Wow, I am not batting 1,000 with this particular video, I gotta say. That means we're dealing with obviously another fault on this board that I so far haven't been able to identify. Now, if you recall, when I got really stuck with TRS-80 Model 3, I worked with my friend David Giller, to come up with a diagnostic ROM for that machine. And I hit him up and I was asking about maybe porting the TRCD Model 1 diagnostic ROM to this. They're not that different, so it should be pretty easy. Well, he did a quick Google search and he actually found something that I think can help us in this situation. And it's this GitHub repo here that says VX200 Restoration. And if you read this, this chronicles this person's journey in restoring their Smith VZ200. And it looks like this was from about 2 years ago, based on the original commit dates. And he talks about the specifications, and there's the machine. Looks like it's in not as nice shape as this one. But here is what's interesting. Remember the Smith unit has 6 kilobytes of RAM plus 2K for the video RAM? Well, it makes it possible using a board, which we already saw because in the schematics it said that there was a separate board for the RAM, and we looked at it and there was an extra LS138 or 139 chip on there. So it obviously connects to the motherboard probably with a pin header, I'm assuming, and contains the static RAMs. Well, in this GitHub repo from about 8 months ago, there's a dead test ROM, a diagnostic ROM for the VZ200 and VZ300, and there it is running. It checks the video RAM, tells you if it's 50 or 60 hertz. It also checks the data lines going to your SRAM on the motherboard. It even tells you how much RAM you have. It says 6 kilobytes here. And we have source code plus some images that have already been created, including the 8K ROM, which will be perfect for installing onto this board. I just dropped it onto a hex editor. Just curious if there's any ASCII. Look, yep, there it is. So this is definitely the assembled ROM. A lot of blank space, but that's fine. It's not very big. All right, I think what I need to do now is I'm gonna flash this onto a 2764 and I'm gonna try to bodge this board so it can accept 2764s. Okay, I have the dead test ROM programmed into this EPROM, and now I need to modify the board to accept the new ROM. So this on the left is the pinout for the 2364, and this is the new one for the 2764. The main changes is that address line 11 was pin 18, that's now pin 23. Address line 12 was 21, now that's on pin 2. What was the address line 11 is now one of the chip select lines, the other one is still chip select line. Then VCC is connected to pin 26 on the new socket, which I don't think really matters, that's not connected. And VPP and VCC, these are already at 5 volts on the board now. And then ideally, pin 27 should be pulled up to VCC as well. That's the programming pin for this EPROM. So what I have to do is either 22 or 20 needs to be grounded, and the other one needs to be connected to the appropriate chip select line. And then I just need to make sure that pin 27 is at 5 volts and that the address lines 12 and 11 are hooked up properly. All right, all the bodges are done, I think, at least. And notice there's no additional wire on the back side, and there's none on the front side at all. I did all the mods on the back. So I figured that they probably designed it to work this way. So I looked for things that were near each other. I compared it to how it was bodged up before, and then I looked at what the various signals were, and I compared them to what's coming off the CPU. So it was a jumper link there, a jumper link there, a jumper link there, and well, that's it. Now, I think I actually found what was wrong with this the entire freaking time. See, this looks like a scuff mark? Well, turns out that this is address line 11. It makes its way over to this pin on the CPU. And I noticed that there was continuity from the CPU to that pin, this is the RAM chip, but there was none to there. And that makes its way to this, and when this is connected together, that basically connects up the address line 11 to the EPROMs. Address line 11. It's pin 23, which is the one I had to fix because with the old ROM, it was connected to address line 12. Well, I think looking at the bodge wires that were on here, address line 11, which used to go to pin 18, I think it was picking it up from right here or right here on the board, and it was disconnected. So I used my engraving tool to scratch away the solder mask, and I could not see a break. It looked complete, but really, I mean, it's clear as day that trace goes from here to there, and there was no freaking continuity. So there obviously was a tiny little break. So I just add a little piece of wire onto there, and now we have continuity. As far as the new address line 12, it was one of the pins that wasn't even connected. So it was one of the pads that was empty. Well, so this pin here, it makes its way over to this via, which goes to there, and makes its way to this pad, which is unused, It's for like a larger, probably that RAM board that adds extra RAM, and then it makes its way right over to the CPU on address line 12. So that was already connected. Oh, and the other thing I just did is I added a tiny little link right there, and that was to connect the programming voltage or hold it up at 5 volts. So 5 volts, 5 volts, 5 volts, and 5 volts. All of this stuff is 5 volts. And I think that is it. And pretty sure that was causing all of the issues with this computer before. And what sucks is we know these are good chips because we could test them in the Retro Chip Tester Pro, but I can't put these back in, well, simply because I've already modified this to take EPROMs. Now, one thing I want to mention about these really cheap PCBs is the solder resist scratches off very easily. So it's very easy when you're reworking the board to create solder bridges between pins. So I used my magnifying loop to go over everything on the board carefully, just to make sure that none of the data lines were shorting out, especially where the traces go between two pins. It's very easy to scratch it away with the desoldering iron, the solder resist, and then create a bridge. And those types of issues have burned me in the past, so I was very careful to inspect the board after this rework. So I have not tested this yet to see if it's going to work. Let's turn it on, and if all is good, we'll get the dead test ROM, and if there's still a problem, we're going to have all that garbage. So here we go, 3, 2, 1. Ah, still not working. Okay, so I'm going to use my little cheat sheet, and I'm going to verify my work going through every connection to the CPU, make sure that they make their way to the ROM chip that's in here. Okay, I checked all my work. Everything seems totally fine. And the only thing that I did is I thought maybe pin 27, which is this /P signal, I had it tied to VCC, and maybe that was wrong. So I removed the little jumper link that is tying that to VCC, and I just left it floating. And let's see what happens when I turn this on. Okay, so kind of random garbage again, different garbage than we had when the ROM is removed, but still random garbage. I brought up a data sheet for the 2764, an Intel one. I looked at one of these earlier to figure out what I should do with that pin. Let's check the Intel one. So the signal pin 27 is /program. And there's a little table here, which we can look at. Yes, for reading, chip enable needs to be low, output enable needs to be low. That's fine. I have those hooked up to the chip select line, and I have it hooked up to the read signal from the CPU. And then the program signal needs to be input high. When you want to know what input high is, we can look down here, input high voltage. It's basically VCC plus 1 volt max. Typical will just be 5 volts. It's TTL, right? But the minimum needs to be 2 volts. So I think I need to put that jumper link back to put that pin back at 5 volts. That is the pin in question. Goes to there, and then there's a little via. But on the other side of the board, because I took a picture, this via doesn't go anywhere. And I wondered why that's not already just hooked up to 5 volts. Well, what would you need to connect that to? I'm not sure. Now, when we look at 5 volts, we have 5 volts on these pins, that pin. There's 5 volts all over the place, but not there. So I'm wondering if they had intended you to install a jumper link to something else. Maybe to there? I don't really get why you'd want to use a jumper link versus just, you could go from there to that pin. But I suppose jumper links are a little cleaner, like these ones, versus going to any of the pins on the socket itself. So I guess I'm going to do it like I guess they intended, and I'm going to put a jumper link from there to that via. Okay, there's the jumper link. That was the most silly one ever, because now these 3 pins are just connected together. Same over here. There we go, everything is connected together. So let's try again. I suppose one thing we're dealing with is I don't know if that ROM works. Maybe it doesn't work on a 2K machine, which is what this is. I don't know. I also wonder if maybe the CPU is somehow bad. No, I don't think it is. Okay, here we go. Let's just try one more time. I assume we're gonna get exactly what we had the first time. So garbage with no flickering. Okay, so let's look at the various signals. This is the CPU read signal. So this comes from the CPU anytime it wants to read from the RAM or the ROM. I have that connected to pin 22 on the EPROM. And this is pin 4 on the 139, which is the ROM 0 chip select line. I think it is. And let's look at the other one. And that's pin 5, which is the signal that's going to ROM 1, the one that's not populated anyways, and it's high. It's perfect, because this ROM, if it's running any code, it should never be calling for the other ROM, since it's not there, it doesn't expect it. I am noticing that I think I did make a mistake. This is the chip select for the ROM that's not installed, which is pin 5 up here. Pin 5 is high, but on the socket it's low. Okay, I made a mistake there. I shouldn't affect anything, obviously, because there's no chip installed there. Otherwise, it would be selected all the time. Let me just quickly investigate what I did wrong. Okay, I see the problem. It wasn't my fault necessarily. It's just this board. There's a bad trace. So this is the signal. That is the chip select. It goes up to this via, and then that makes its way through this trace to there. And this is going to pin 5 on the LS139. But notice there's no continuity. Now there is a via. Now I put a little jumper link there to bridge this to the via that was right next to it. But the pad came off. And I think what happened, I need to scratch off some of the resist. I think what happened is it's just not making good contact. Again, because that chip is not being used right now, it doesn't matter. This isn't actually going to have a negative effect on anything. But let's just make sure that this is connected properly, which I hope it should be now. So this should go to pin 5. It is indeed. So that does it via this. Yeah, okay. So I just had a bad connection because of the bad pad that was there. But that does not help me understand what's going wrong here. Because I've never tested this ROM, I'm going to actually find a copy of the original ROMs and I'm put them on EPROMs and reinstall them into the board. This thing may be working at this point. It's just this dead test ROM might not be. All right, I think these are programmed properly with the correct ROMs, I think. This is U09, U10. I think that's right. I might have to swap them around. All right, let's give this a try. 3, 2, 1. Oh, interesting. So not working, but different. Not working, but different. And it looks like the system is stuck in a loop very similar actually to the dead test ROM. And the second ROM has no activity on the chip select line, but the first one has the very, oh, it looks so similar, doesn't it? Just for grins, I'm going to swap out the CPU because I can. Okay, the other CPU is in. Let's see if anything looks different. I'm not holding out hope. I still think the CPU is good. Okay, well, it looks different, which is odd. I don't see why it should look different. I put back in the dead test ROM, just because we swapped the CPU. Oh, it looks exactly the same as it did when we had this CPU in. Now, the dead test ROM, by the way, I looked at the documentation. It says it really doesn't even need the RAM. It just needs the ROM working, the video chip, the clock, reset, you know, the simple stuff, and the CPU. And obviously the ROM chip select line to be working. But as we can see, that is not the case here, at least. All right, I think I'm going to stop this video here. I'm stuck, obviously. I'm going to look into this dead test ROM. Since the source code is there, I need to at least see what it does when you first power up the machine. Ultimately, I would hope that something like a dead test ROM would, at the very beginning of execution, try to show that there was some sign of life on the machine. Beep the speaker, clear the screen, something like that. Maybe this ROM does that. I don't know. But I really do need to look at the assembly code just to see what this thing is trying to do. And you know what? If this ROM doesn't do that, then I think I'm going to try to write my own, even just to do the most basic thing like beep a speaker or clear the screen, put a little bit of text on screen, and then go into an infinite loop. I just need to know if this thing is executing code or not executing code. And so far, I do not know if it's doing that. None of these ROMs that we're testing, well, give me any kind of signs of life out of this thing. Everything is different when I change the ROMs, but I don't get the actual sign of life that I need to know that the thing is working. So if you have any thoughts about what I've missed, and you've been shouting at your screen the whole time watching this video, please comment down below. Let me know, because I am quite stuck here. I hope this video shows that even when a computer like this, which seems very simple on the surface, doesn't necessarily mean that it's easy to fix. I know there was at least one broken trace on the board, and maybe there's more. And when you have broken traces, that can be pretty tough to diagnose. There aren't silk screen markings on this thing to even identify which chip is which. And the schematics are obviously for a slightly different revision of the machine, which I think should be all the same except for that RAM board, but I'm not totally sure actually. So anyhow, I'm gonna leave it there. Thumbs up if you liked this video, thumbs down if you hated it, comment down below, subscribe, all the usual YouTube stuff. Huge thanks to my supporters, their names are going off the side of the screen. They make it possible to do this full time. You can become a supporter too if you'd like. And I think that's gonna be that. So stay healthy, stay safe. I'll see you next time. Bye-bye.